report on this computer. Okay, so the last thing we talked about, let's just touch base with what that was. We were looking at the Binet formula for the Fibonacci sequence and the Binet formula for the Lucas sequence. And we noticed all sorts of groovy stuff. Like, well, for instance, the Lucas numbers are always bigger than their Fibonacci counterparts. And the elephant in the room that I want to speak about today is this thing. This thing over here. The 1 plus square root of 5 over 2. This is a magical, beautiful number that we're going to be calling phi. Phi in Greek alphabet is written like that, or the capital letter like this. And this is a irrational number. It's approximately 1.618. It is very beautiful in the following sense. It's the only number that when I take the reciprocal, 1 over phi, I get exactly the decimal part. So let's look at that with Desmos. That's easier to see with Desmos. Did I show this yesterday? I'm having a brain fart.
No.
Okay, good. Desmos. So 1 plus the square root of 5, what's that? There's one way to get square root of 5. Over 2 is this number, 1.618033989. And if we let's take this number and let's look at the think of the reciprocal of this number. I'm gonna half screen this. Let's think about the reciprocal, 1 over phi. 1 over phi. What is this equal to? Well, let's go to a new line. 1 divided by phi is 0.618033987. And it goes on. It has infinitely many decimal places. It never repeats. This is a famous irrational number. But what's interesting about this is that if we compare the digits here of phi, 1.6180339, and we compare the digits of the reciprocal, we get exactly the decimal part. So we get exactly that phi minus 1 is identically equal to 1 over phi. You'll never find a number like that. Phi is the only number that has that property. And so, like, let's think about numbers that are really close to phi, like 1.1 over 1.6, and then we have 1 over phi, and then we have 1 over 618. Let's think about 1.6, a number that's just a smidge bigger than 1.618. How about 1.62? So let's think about these reciprocals, like 1 over 1.6. This is pretty dope. Hang on to your hat, especially you, Stefan, since you're absent today. 1 over 1.6 is 0.625. 625. Now let's go down here to 1 over 1.62. And notice 0.625 is strictly greater than 0.6. Well, what about 1 over 1.62? Let's put a 2 here. Then we get that this number is equal to 0.617, 617, whatever, other stuff. And that's strictly less than 0.62. So something is clearly happening here in what we call the sweet spot. If we look at these two denominators in between 1.6 and 1.62, in that tiny little smidge of space, there's exactly one number such that 1 divided by it is exactly equal to the decimal part, 0.618. So 1 divided by 1.618 is exactly equal to 0.618, but not just those 3 digits, but infinitely many. So that's one reason alone why phi, the golden ratio is like out of control, bizarro, weird. And your faces are not doing what I was hoping it was doing. Ryan, make the face of like disbelief and wonder at the same time. Well, I'm seeing wonder, but not disbelief. Too much disbelief, more wonder. Okay, but disbelief and wonder is what this is supposed to conjure. This is weird, but this is only the tip of the iceberg. I'm gonna get even crazy weirder because this number is so unique in mathematics. It is like a freak of nature, but people love it, you know? You know, sometimes unique things are not adored because everyone's like, be the same, and B is so freaking different. Who's that guy? Okay, so the golden ratio, where does it come from? Where does this number, where does it come from? Well, everything is a solution or a root, that's another word for solution, to equations. So I claim that this is a root of the equation x squared minus x minus 1 equals 0. So let's recall the quadratic formula. If you have ax squared plus bx plus c equaling 0, then the two answers, or the two roots of the quadratic equation, the two solutions, is given by x equals negative b plus minus the square root of b squared minus 4ac all over. Cool. Y'all are like opera singers. Okay. So
Thank you.
we have this quadratic. A is clearly 1. B is clearly negative 1. C is clearly also negative 1. So now let's do some quadratic action. So the two answers are given by x equals negative 1 plus minus the square root. I'm not going to sing anymore. B squared is negative 1 squared minus 4 times 1 times c, which is negative 1, all over 2 times 1. Okay, so that's a mess of numbers. Let's clean this up. Negative and a negative 1 is that negative times negative 1 is positive 1 in the numerator. And then plus minus the square root. What's inside the square root? Well, we have negative 1 squared, which is 1, minus 4 times 1 times negative 1, so that's positive 4. So 1 plus positive 4 is 5. And then divided by 2 times 1, in other words, 2. So the answer is, there's two answers. One of them we're going to call phi, which is the positive solution. And then the other solution is negative. Why do I know that? Because the numerator is negative. The square root of 5 is strictly bigger than 1. So the numerator in phi tilde is negative. So this number is negative, this number is positive. And so those are the two numbers that come up into the Binet form, i.e. the closed form of the Lucca and the Fibonacci stuff. Those are where those two numbers can come from. So, of course, if we see the golden ratio inside the closed form of the Fibonacci sequence, that must mean there's some intimate connection between Fibonacci numbers and the golden ratio. And that connection is beauty. And it all starts with a line. We have a single line. And I'm thinking about this line. There is one sweet spot. There's one sweet spot in this line where if I cut it right at that point, that exact point, let's think about the line being this whole thing, this whole thing here. There's one sweet spot. So the sweet spot here, sweet spot, where we can cut it so that the whole line, which is length a plus b, divided by the big chunk. So the ratio of the whole line to the big chunk is equal to the big chunk over the small chunk. So that's called, well, I forget exactly what how geometers call that, but it's the ratio of the whole to the big is equal to the big to the small. And there's only one place in any straight line where we can cut that. So if we call the length here phi, and we call the shorter length 1, and then we make it into a rectangle where phi is that length and 1 is that length, we get something called the golden rectangle. The golden rectangle, mathematically defined, is the prettiest rectangle that your eyes can perceive. The Greeks took this a little bit too far by like making every single building in antiquity have the dimensions of the golden rectangle. The Parthenon of one building that's exceptionally big as that. And every single little statue in the Parthenon is in the dimensions of the golden ratio, either like that or like this. And the golden ratio will have like a bunch of little figures of angels and gods and all that, and they're all like in the dimensions of the golden ratio, because they wanted stuff that was just extremely pleasing in the scientific sense. It's easier to look at, and that's where we're going to get into this stuff eventually. So let's derive the following. So I said this on the previous page. I said the number 1.618. Remember, it's not, that doesn't end there. It has infinitely many decimals. Is equal to 1 plus 0.618. So when we prove that this part here called 1 over phi is just 0.618. Well, let's use this thing. And by the way, this is correct here. The ratio of the whole A plus B is to the big chunk A, as the big chunk A is to the smaller chunk B. But here I accidentally put a B. So this is a typo. It's an embarrassing typo because it doesn't make any sense. The ratio of the big thing to the big chunk, not B. B is the small chunk. We want the big chunk. So, where should go? I don't know what it is. Okay, so let's let A equal phi, and let's let B equal 1, and let's compute these two ratios. So A over B is phi over 1. And what do we have? We have A plus B over A. Well, let's substitute what we know for A. A is phi and B is 1. So we have phi plus 1 over phi. We're just replacing A's with B's and B's with 1s. Seems a little dark. Okay. So if we're going to set these two ratios to be the same, then that means that phi over 1 is equal to phi plus 1 over phi. So this implies then that this ratio, phi over 1, is equal to phi plus 1 over phi. Now hold on to your socks, even if you're not wearing any. What is this fraction? Well, I can write the right side as 1 plus 1 over phi. I just split up this fraction into phi over phi, which is 1, and 1 over phi, which is that. And on the left, I can get rid of my denominator because it's not really there. And voila, this is a proof that the reciprocal of 1 over phi is the decimal part of 1.618. Just that stuff, the decimal part. And that's beautiful. That's beauty number 1. Now let's multiply both sides of this by multiply by phi. We're going to multiply both sides. Why? Because we can. So on the left side, we get phi squared. On the right side, we get phi times 1, which is phi. And then phi times 1 over phi, well, the phi's will cancel, leaving us 1. So this is another miraculous thing. I dare you to find a number whose square is also 1 more than that number. There's only one magical number in the whole entire universe or multiverse such that this occurs. It's a freakish anomaly. Like left of phi is just a phi's over here, and then we have the number 2 and number 1 here, for instance. If I squared 1, I'm not going to get 1 plus 1. If I square 2, I have 4. I'm not going to get 2 plus 1. Somewhere in between 1 and 2 is a sweet spot, and that sweet spot is called the golden ratio. The golden ratio is the only number on which, if you square it, it is 1 more than itself. But that's not even the beginning of it. I can't curse because this is on YouTube, and it's illegal to curse on the web. Unless I take the child settings off. Okay, hold on to your poop in your pants because it's about to come out. Let's multiply this by phi. Oh, I smell it. Someone's let it go. Okay, I haven't even given the result yet, and already you're pooping your pants. This is amazing. Okay, phi times phi squared is phi cubed. That's no surprise. And then I'm going to multiply all this. This is phi squared plus 1 plus phi. If I multiply the right sides by phi, oh, this is a badly drawn phi. Okay, here we go. But we have already asserted that this phi squared is phi plus 1. So what we really have here is I have that phi cubed is phi plus 1 plus phi. In other words, it's 2 phi's and 1. So phi cubed is 2 phi plus 1. So we have 3 amazing facts here. Amazing. And we can multiply the bottom box again by phi. We'll get phi to the 4th, and then we'll get this on the right will be 2 phi squared, and this will be a phi here. And if we settle the dust, all the coefficients will be Fibonacci numbers. The Fibonacci numbers show up in all the powers of phi. And it's just weird. But now it's going to get even weirder. I mean, actually, it never stops getting weird. Let's draw something that I want you to worship eventually. So above the doorway at Plato's Academy, Plato's Academy was a place where Plato, the philosopher guy, hung out with other guys in togas, and all they did was sit around and, get fed grapes by scantily clad other guys who fed them grapes and fanned them with big fronds. But then mostly they talked about math. But the symbol above the doorway was this. And then it said, let all ye who enter here, blah, 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 something. Understand this thing. Understand deeply what this pentagram means. And so, if we let this length be 1, this length here, if I drew a perfect pentagram, which I obviously didn't, because the pentagon inside there should have all the same length sides. This side looks bad. I probably should have just put one in there that was made by a computer or something. But if this is length 1, if you drew a perfect pentagram, then this length turns out to be 1.618. So embedded in the pentagram, not just Plato's pentagram, but anybody's, so any pentagram, is golden ratio can be found if you set this length to be 1. This length is phi times whatever this length is. So it's this line then, this line here in between my index finger and my thumb has a golden cut right there. That's the perfect ratio where the whole line's ratio to the big chunk is equal to the big chunk divided by the little chunk. But it doesn't end there. This is also phi, and this is also 1. So, so this thing now that I'm highlighting in red, that's phi plus 1. But phi plus 1 is, oh, so this length is phi squared. The fun doesn't end there, because we also have this length here. This length, well, all of the stars pointing out are length phi. There's only 2 lengths here, phi, those pointing out, and then the ones in the pentagon, the length of 1 in the pentagon inside the star. So what do we have here? There's lots of ways to look at this whole chunky line, the one that goes from here all the way down to there, that length. That length is phi squared plus phi, or I can view it as phi plus 1 plus phi. But where did we see phi squared plus phi? We saw it right there, phi squared plus phi. And where did we see phi plus 1 plus phi? It's right there, phi plus 1 plus phi. So this big chunky thing is actually phi cubed. So there's layers upon layers of perfection and beauty in this thing with golden ratios, all the freak over it, like everywhere you look. Actually, this angle is a golden angle, and that's a whole another topic. Truly, a talk about the golden ratio should take the whole semester if we were to study this in depth. The amount of mathematical literature on this one single freaking number called phi is intense. Because of, well, this is just the tip of the iceberg. And the rest of the iceberg is the thing that, it's just an iceberg full of polar bears. It's groovy. Super wonderful. And then if you turn it upside down. Ha, ha, ha. Ha, ha, ha. Perfect, there. Okay, sorry. Well, actually, even this way. Perfect, there. I suggest you get a tattoo of this on your booties because it is, it's the thing to tap. Don't get like a tattoo that says a flower and then says mom with a heart. No, you get that pentagram. Guess something about a mom with a heart, or?
What was the significance of the, go down again? What was the significance of the thing on the bottom,
Oh, the golden angle?
yeah?
I didn't want to talk about that,
Okay.
but, it's another thing like the golden ratio, but now it's for angles.
Okay.
It has incredibly insane properties, and actually it has weird connections. I gave a 45-minute talk about connections of the golden angle and the value 666. Also crazy intimately connected with trigonometry. And that's no accident. There is an embedding, there's a connection between the value 666 and certain trigonometric values of the golden angle. But if you're interested in that, come to my office and we can not worship the devil, but see why that number is relevant. Okay, golden ratio continued. Does the golden ratio appear everywhere in nature and man? Well, it does. A lot of pop culture books talk about how it is all over nature, and it's not. It's sad that it's in pop culture because it's true. Like on the pineapples and and flower petals always come in numbers that are Fibonacci numbers, and then the golden ratio and Fibonacci are embedded together. But it's let's talk about the golden spiral. The golden spiral is created by the golden rectangles. If we look at inside here, we're constructing rectangles inside the ear of this person we'll call Sam or something. I don't know, something. Yeah. So we have inside here, this rectangle is length 1 and 1. Maybe I should just draw with a little blow up. 1 and 1. So it's a square of length side 1. And then on top of that, I'm going to put another square of side 1. And why am I doing that? Because let's think about the Fibonacci sequence. So these lengths all have length 1. But if I look at this as a rectangle now, it has height 2. So 2 is that next number. So I'm going to make a square on the left here, height 2. So all the sides have length 2. So now this new rectangle we produced is length 3, because this side is length 2, and then that side is length 1, so its sides are length 3. So on top of that, I'm going to put the third Fibonacci number in the form of a square, a 3 by 3 square. 3 by 3. And that's that rectangle up there on the left side of Sam's ear. Okay, I don't know this guy's name, so I'm just going to say Sam. That's a good name. Oh, wait, no, we should choose a different name. Okay, Callie, Shirley, Carol.
Shirley was, I like Shirley.
Shirley, okay, Charlie, okay, Shirley it is. And then, and now this length is 5, obviously, which is that next Fibonacci number. So we're gonna stack on a 5 by 5. Uh-oh, bad idea, Alba. I'm at the edge of the page. 5 by 5 there. And now this length is clearly 8 at the bottom because we have a length 2, a length 1, and a length 5. That's length 8. Then we chunk here. And what we're doing as we do this, we're getting closer and closer to the dimensions of a golden rectangle. The golden rectangle, remember, is the one that had the ratio of the big part over the small part is exactly the golden ratio. And so we're saying the number 8 plus 5 is 13 divided by 8 is approaching the golden ratio. And if we do this infinitely, and then also if we do this infinitely, we're going to get, well, an infinite size rectangle. But if we go to the top, we trace a spiral in here. This is how we construct the golden spiral. And what's nice about the golden spiral, it's microscopically in the Earth. It's macroscopically in the universe, like the Milky Way's elliptic galaxy. There's these. If you look at images of how the stars are clustered in our galaxy, they are on these spirals that model exactly the golden spirals. And that's no accident. And also clamshells, the shells of some snails have the golden spiral in them also identically. And it's said, and this is now an opinion, that people like Shirley here, are more beautiful if they exhibit such golden properties. And this person is perfect. Shirley is like dope. In fact, who wants to be Shirley? Honk if you want to be Shirley. Huh? There's a lot of honking. There's a lot of honking. Okay, honk honk. Okay. So we're gonna move on. I do actually believe I know this face. I've seen it before. I just can't put a name to it. Okay, and here's another Shirley. This Shirley was drawn by who? Huh? Shirlinky? Oh, Da Vinci. Well, let's say Leonardo, because that's the first name in Fibonacci. Sorry, there's nobody named Fibonacci, but Leonardo Pisano is his first name is Leonardo. So Leonardo da Vinci drew this thing, and the golden spiral fits here, but it's also mostly the golden ratio is all over this in terms of the distance of where the golden cut, I believe, is at the bottom of the nose here. And so this length, the whole length of the face divided by the length of that to the nose is the same as the big chunk to the small chunk. And it happens in the eyes and individually in the nose, and also it happens in the man of Vitruvius. You might know that as the naked man, man of Vitruvius. Sorry. Well, yeah, sorry. There's not the naked man. Sorry, one of Vitruvius. Images. So the man. Oh, wait. Okay, you know this thing's got to go. Whatever this thing is. Okay, you got to go. You got to go.
Spiral.
So let's pick one that doesn't have a penis. They usually like take it out on some of the photos because we want this to be a, you know. Here we go. This one's like devoid of. Oh no, there's schlong there. Well, it doesn't matter. Doesn't matter. But what we're seeing is the dimensions. There are golden cuts all over the arms, golden cuts all over the body. I believe this is the golden cut here, or maybe that's the center. But the man of Vitruvius is supposed to be the perfect man. And so, hey, stop focusing on the dead center. Hey, stop focusing on the dead center. Come on, this is a math class.
The mouse.
This was an art class, you can focus on the schlong, but this is a math class. All right. All righty. So let's look at nature now. Nature. This is what a lot of people talk about often in pop culture. The sunflower. When you look deep in a sunflower, it looks like this. And you probably didn't ever care to like consider it, but it's kind of there's two sets of directions. There's like arcs going clockwise, and then against that there's arcs going counterclockwise. The number of arcs going clockwise and counterclockwise are neighboring Fibonacci numbers. They're not necessarily 34 and 21 all the time, but if they're not 34 and 21, then they're 55 and 34. And if they're not 55 and 34, then they're 89 and 55. But it's something worth counting. For whatever reason, whoever constructed this universe likes the golden ratio, and whoever constructed the sunflower in particular is not trying to hide it. Yes. And this is center, is that a daisy? Oh, maybe. Okay, sunflowers do the same thing. You know what? I'm from New York. Can I just get a pass?
I suppose.
All right, you know.
Read
It's concrete
not
jungle.
here. She can't change it.
It's just not yet. You see researchers, you can't.
But
Yeah.
so next time you look at a daisy, maybe you should go counting these things. All right, and then the ratio 35 divided by 21 is 1.69.
Wow.
And no, that's not a wow. Wow is about to come. But yes, that is nowhere near the golden ratio of 1.618. But check this out.
Wow. That'd be woo.
So let's think about the ratios of F and neighboring Fibonacci numbers. So F9 is, well, 55 is F10. F9 was 34. 89 is F11. And 144 was F12. So let's look at F10 over F9 using, which is 55/34, using Desmos. Using Desi, let's get Desi on board. Where are you, Desi? Over here. Where? Over here. Oh, hi there. Hi. Okay, so, we're thinking about 55/34. And we get 1.617647059. Maybe we should remind ourselves some values of phi. 1.618. I'll go up here. What happened? Control Z. I know what happened. Where's our golden ratio? 1.618033989. 033989. Okay, now let's go back to the bottom, and now let's look at another ratio. How about F11/F10? Now, GZ, get ready. This might be more interesting. 89/55, and 89 and 55 in terms of daisies is realistic. They have appeared, they have been counted and noticed and observed. So 89/55 is a repeating decimal, 1.61818, like that. So notice that this number here is strictly less than the golden ratio. This one here is a smidge bigger, but closer to the golden ratio than this number. Oh, sorry, we can't see that. So now let's do F12/F11. And this is 144/89. Again, hold on to your poops again, because this is going to be groovy. Oop, I think I smelled someone farted. Okay, yep, this is good. 1.617977528. This is just a smidge smaller than the golden ratio. So as we do this, we're getting closer to the golden ratio, but we are flip-flopping. We're under it, over it, under it, over it, but we're getting closer and closer to it. So as we tend towards infinity, we are getting that Fn plus 1 over Fn is going to move exactly to approach to be as close to the golden ratio as you desire, with as many decimal places that you'd like. And so that is some reason that people who study beauty believe that the concentric spirals inside a daisy are why daisies are beautiful, basically. They imply the golden ratio by the ratio of the spirals going one way versus the spirals going the other way. So that was pretty fun. Now let's get into some applications. None of this is applications. This is the application of everything I showed you up to now is beauty. Now let's talk about a problem of climbing upstairs. Okay. So how many ways to climb up 2 stairs if you can only take 1 or 2 steps at a time? So let's draw 2 stairs. So this is the ground level. So no stair there. That's the 0th stair. So the first stair and the second stair. So we can only go up 1 step at a time or 2 steps at a time or a mix of them. So here we're going up 1 step at a time, and then we do that. That's one way to do it. Another way to get up to the second step from the 0th step is to take a step of size 2. Wow. And is there any other way to get to the second step? No. So there's 2 ways to get up 2 steps. About 3 steps. So let's add 1 to this in a new picture. 3 steps. We get wow, 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 wow. Okay, one way we can take single steps the whole time. So boom-pity boom, and boom-pity boom. That's one way. So we can draw another one of 3 steps. Another way is maybe I can take 1 giant leap first of a 2-step jump and then a single step. Now, we can't do 3 steps at a time. We're taking only 1 step and 2 steps. So that's another way. Let's try to see how many other ways there are possible. How about if I take the small step first and then I take the double step? Now we just think exhaustively. Have we exhausted everything that we can possibly do? We can't take 3 steps, and we can't take no steps. So one can say, just take the elevator. So there are three ways. So if there's two stairs, there's two ways. There's three stairs, there's three ways. If there's four stairs, there's five ways. You would expect the number to be 4. But why isn't it? Why isn't it 4? This pattern is weird. 2, 3, and then 5? Or is it weird? Fibonacci! Yes, Fibonacci skips 4. Remember? 1, 1, 2, 3, 5, 8. You know, so we can imagine if there's 5 stairs, there's probably 8 ways, you know, the next number. Yeah. So another way to think about this is called integer partitions. This is a course in grad school all itself, partitions. People who study number of ways I can have the number 4, and I want to add up sums of numbers using only a subset of choices. Here, we're saying if we only have the numbers 1 and 2 available, and I can add them up to get 4, I can say 1 plus 1 plus 1 plus 1, or 2 plus 1 plus 1, 1 plus 2 plus 1, 1 plus 1 plus 2, and 2 plus 2. And finding out like how many, if the number was, how many ways can I add up the numbers to add up to 100 using 1s and 2s? That's a really hard problem. But it turns out that the number of ways is a Fibonacci number, because this problem here, counting the integer partitions of the number 4, is the same as the question of counting the ways to get up to 4 stairs when you can take single or double jumps alone. And the answer is the 5th Fibonacci number is the number of ways to get up 4 stairs. So let's exploit this in the next part where we have an exercise. How many ways to climb up bold n stairs? You can only take 1 or 2 steps at a time. So we're going to let the answer be called y sub n. The number of ways to climb up n stairs, if you can only take 1 or 2 steps at a time. For example, we learned on the previous page, if there's 2 stairs, then we have y sub 2 equal 2. If there was 3 stairs, y sub 3 equal 3. If there was 4 stairs, y sub 4 equaled 5. And we know that here, y sub 2 is f3, because f3 is the number 2. Here we have the 3 is f4, so we're saying y3 is f4. f5 is the number 5, and we're saying that y sub 4 equals f sub 5. So the conjecture for the answer, the number of ways to get up n stairs is equal to, yes, the number of the subscript is 1 bigger than the number underneath the y. So f n plus 1. So sadly, we have to call that a conjecture, even though it's extremely true by a few examples, and it feels like it would be true. If you'd like to know how to prove this for sure, come to my office hours and we can prove it together using high-powered mathematics. Actually, not even high-powered mathematics for some of these. How many ways to climb up 49 stairs if you can only take 1 or 2 steps at a time? So we're searching for y sub 49. How many ways can we do that? Did we learn anything from the box? Yes, we did. Rosa, how many ways can I do that? 49 stairs using the conjectured formula?
49 plus 1.
Yes. Well, that's the subscript. So you mean
4.
F? Yes. Just say 50. You don't have to say 49 plus 1. 49 plus 1 has a nickname. People have been calling it 50 for like a long time these days. It's all good though. Shirley invented that, by the way. 49 plus 1 equals 50 when they were in office. Sorry, I'm getting political, but that was one of the things that they did. Okay, so let's compute that. Is that going to be a big number or not? Well, we have a Binet formula. Oh, geez, I don't really want to type it in, but I could do that. I don't want to type it in. I can do it. I can do it. Square root 5. And then the formula had minus the same thing. And then inside here was the golden ratio. I'll just steal it from here. Wow. We have the golden ratio, and we had the golden ratio's buddy with the negative here. And then we need exponents. we'll put 49 here. And then we'll put it over here and put 49 in this exponent. 49 and oh, my bad. Yep. I was caught with the subscript of y. Thank you, Lyric. You are a savior. Not to be confused with the Son of God, but same thing but different. Okay, so we have a number that is ginormous. I can't give you the exact number because Desmos is being a punk, but it's a 1 followed by 10 zeros. So that's 10, 6 zeros is a million, 9 zeros is a billion. So a little, approximately 12.5 billion. There's 12.5 billion ways. There's 12.5 billion ways to get up 49 stairs. So you know what you should do after class? You should check this answer by going up 49 stairs and counting all the different ways. I bet you'll probably do it before your great grandson is dead. You can finally finish it before that. Oh wait, you can't peace out, Girl Scouts, yet because actually maybe you can peace out, Girl Scouts. That's a term, right? Okay, all right. On Friday, we'll say what happens when we just start with any two numbers. All right. There's homework due tonight on what? 11.1, and then tomorrow's homework on Fibonacci. You know everything to do that homework. There's not a single question that's like this stuff here on the generalized Fibonacci sequence. So, thank you for being bomb. Oh, you're on TV.
No.
Okay. Yep.
Oh.
Goodbye, the class is leaving. Thank you for watching the video. Love the golden ratio.
I'm just gonna add one of my phone if I have 18 credits. Like 18 credits.
Anyway, right to the camera, Kendra. Rick, say goodbye to the people. America's watching. Come on, say goodbye to America. Lydia, say goodbye to America.
Bye, America.
Oh, actually, this is the internet. Say goodbye to the world.
So, well, see ya.
All right, see ya. I think you talk about it right now, but I haven't prepared for my passport class.
I'll get golden ratio stuff,
It's just that sequence stuff.
sequence stuff.
Well, they're embedded together, like the
That's why I want to learn more. They're embedded. I know golden ratio. Don't know.
over there on Friday. Should be a hoot.
Okay. We haven't talked about the golden ratio.
I did in topic gave on 666. No video on it because I gave it in seminar room before video was a thing. This was like back in 1680.
It's a shame, it's really intriguing.
All right, wait. Say goodbye to the world, Catherine. I'm gonna turn it off now. Catherine says goodbye. And you want to say goodbye together to the world? Okay. Goodbye, world. I just love video. I can't believe it exists.
Bye.